So we're looking at beta decay, and the beta decay is a bit of a weird one because we're going to look at alpha decay afterwards. But for now, let's just look at beta decay because it's the weirdest of the decays. Basically, for a start, any type of radioactive decay is when a nucleus of one atom changes into a nucleus of a different atom. So, as far as we're concerned, that's very odd already because these are supposed to be elements, which mean they're all made out of the same type of atom, and so the atom has somehow changed into a different form. Now, because we've learned about atomic physics, we've learned about the structure of the atom. We know that that all atoms are made out of protons, neutrons, and electrons. We're only interested in the nucleus, so if we just below, we've got a diagram of this carbon-14 nucleus. It's also worth saying at this point that a carbon-14 nucleus is different to the one that we see on the periodic table because it's got more neutrons, but it's still carbon because it's got 6 protons. What happens is it changes into this nitrogen-14 nucleus. So basically, a neutron turns into a proton and also gives off something called an electron, which we call a beta particle, and something called an antineutrino. We won't bother talking about the antineutrino at this level, although it does come into play A-level physics. But the electron appears. And so we can look at a more simple level. We can say that all beta decay is just this. A neutron turns into a proton and an electron. We call this electron a beta particle because it's not just any electron. It's an electron that magically came from a neutron, which is kind of weird. So first thing to think about here is that we have learnt that the mass of a neutron we say is one. We say 1 atomic unit. And that's also the mass of a proton, 1 atomic unit. Now, this would mean that because an electron is not 0, the mass is not 0, then we have seemingly created matter from nowhere. There's 2 answers to this mystery. The first one is that neutrons and protons don't weigh exactly the same as each other, but very, very close. And electrons are very, very light. And so the difference could be the mass of an electron. But that isn't actually the total answer. Hang on a second. So that's part of the reason. Part of the reason is that the neutron and the proton are very close to similar mass, and the electron is very, very light. So although it doesn't equal 0, it actually is very close to 0. So that means like roughly equal to. So in that sense, it's fine. However, there is another problem. There is another reason why the math still adds up, and that is because of something that Einstein said, which everybody's heard of, which is E is equal to mc squared. So let's just recap. What does this mean? So this equation is just saying that energy and matter can be converted. So it is possible to convert energy into matter and matter into energy. And when you do, they can be calculated using this equation. So let's say that I had 1 kilogram of matter, and I turned it into pure energy, then the value of that energy would be equal to that 1 kilogram, so 1 multiplied this c squared. So c is the speed of light, and what some people get confused with is we've got to somehow imagine that the thing that is moving at the speed of light or something like that. It's nothing to do with that, really. There's a reason why it's the speed of light, but basically just think about it as just a number. So it's multiplied by a number which just so happens to also be the speed of light. So it's multiplied by. So basically, because E equals mc squared, what this means is that energy and matter can be converted. So the difference in energy, if there was a difference, so basically, let's imagine that we added up the mass of the neutron and we so that was the energy at that was the mass at the beginning. We would have expected that's going to equal to the mass of the proton plus the mass of the electron. And if we also we talked about the antineutrino earlier on, didn't we? So the mass of the antineutrino as well. Now it might be that it doesn't. In fact, it definitely won't equal that, because also some energy is going to be produced. So that's going to actually be equal to. It's going to be equal to, yeah, exactly. So by rearranging this, you would say that we can see that would be, the mass would be equal to energy divided by the speed of light squared. So then we would say it's going to be equal to the energy that was given off divided by the speed of light squared. So there is going to be a slight difference in energy. Most people don't think about it, notice that actually. So, but if you do, if that does make you wonder, that's the explanation. Obviously, this won't come up in GCSE. It does come up, I think, well, maybe a tiny little bit. They kind of mention it very, very vaguely about at some point to do with radioactivity, but I don't think I've ever seen an exam question on it. It does come up at A level a little bit here and there, but again, not that much.